Again, question number one. So question number one wants us to know the resistant and non-resistant measures of center and spread. So the first question wants us to sketch a skewed left distribution. So a skewed left distribution will look something similar to this, where a lot of the data set at the beginning of our of the representation of our x values will be on the lower side, and as we move more and more to the right side, that's where a bulk of our data set is. All right, so it's at the end of that tail. Okay, so right here is where the skew, and this will be considered skewed to the left. Okay, in relation to a skewed left distribution, what's the relationship between the mean and the median? Well, whenever we have a skewed left distribution, the mean will always be less than your median. All right, well, why is that? Well, because most of our data set is shifted more and more to the right side, okay, our median or middle value will actually be what is more and more being impacted or being moved, okay? Our mean will stay a little bit more on the constant side, but because we're shifting the median a little bit more and more to that end tail, all right, that will essentially impact what the median will be or how large the median will be, okay? So next, which measure of center and spread should be used? Well, in relation to a left skewed, okay, for center, the best representation is your median. Well, why is the median the best representation for the center? Well, the median is the only thing that will be non-resistant to any outliers, okay? So if I was supposed to take away a value from here or here, essentially your median will stay almost unchanged, okay? For spread, the best representation for spread will be your IQR, and you find your IQR by doing Q3 minus Q1. Well, what does that really do? That Q3 minus Q1, Q3 correlates to 75% of your data set, Q1 correlates to 25%. When we subtract those, we're only looking at 50% of the data set, but that middle 52, which gives us the general trend of variability. All right, so the IQR is the best representation. All right, the next question. So the next question wants us to utilize operations that affect the mean and standard deviation of data sets. What you should know is that whenever you're mixing two separate data sets, the mean can correlate with each other, can commingle, but your standard deviations cannot, all right? So that means I can add or subtract my mean together for a different data set, but I can't do the same thing for the standard deviation. So let's start with the first question. What is the mean and standard deviation of 4a minus 10? Because we're looking at set A only, we don't need to evaluate any commingling of standard deviations. We can just calculate as such. So I'll do 4 parentheses, replace the A with the mean for A, which is 12, then minus 10. 4 times 12 is 48, minus 20 is 38, okay? I would do the same thing for standard deviation because, again, we're not mixing the data sets, all right? So I use the standard deviation for set 8, or set A, which is 8, okay? Then minus 10, 4 times 8 is 32, 32 minus 10 is 22, okay? For the next one, what is the mean and standard deviation for 2B? Because we're only focusing on one set, we don't have to evaluate any commingling of standard deviation. So the mean you can calculate as 2, replace the B with the mean for B, which is 20, all right, which will give me 40, okay? And then I do the same thing for the standard deviation for B, which is 6, and the answer will be 12, okay? Here, it says find the mean and standard deviation of A minus B. Here, we're doing some type of commingling between two separate data sets. For the mean, that will stay the same. We can calculate it the same. 12 minus 20, which is negative 8. However, for standard deviation, you have to utilize something similar to your Pythagorean theorem. All right, which is just the square root of the standard deviation of A squared plus the standard deviation of B squared, okay? So when we calculate this, the standard deviation of A was 8, so I'd have 8 squared, plus the standard deviation of B, which was 6, so that's 6 squared. This will give me the square root of 64 plus 36, which is the square root of 100, which is 10. And you're probably wondering, well, why are we utilizing this and not just plugging it in? Well, whenever you're trying to find any difference, whether positive or negative, between two separate sets involving their standard deviations, the variance of it is what comes into play. To evaluate the variance or the change in variance, you have to do something similar to the Pythagorean theorem. Okay? Now the next question. So the next question says we're trying to use a linear regression equation to describe a residual given the data points. So it says the mini table output below is an LSRL analysis. LSRL stands for least squared regression line. Okay? To predict the grade on a test based on the study time. Because it told us that we're doing their grade based on the amount of study time that they did, okay, the study time will be what's essentially going to change, or your explanatory variable, okay? Because if you study more, you should get a higher score. That's what we're stating, okay? So based on that, your response variable, what's going to respond, will be your test grade. Because your test grade will get the impact based on your study time, okay? So now we need to formulate that equation for the LSRL given the stat output. Given the stat output, you're going to look at area that has the coefficients, because those give you the values for the slope and the y-intercept. So we're going to have y hat. We use y hat because that represented the predicted value for y, is equal to, so now I need to identify my slope. To identify my slope, I need to remember what's going to be changing. So what's going to be changing is the study time, because if I study more, that's going to impact the test grade, okay? So essentially, what correlates with that will be the 0.8, and that 0.8 will represent your slope. So if you study by any amount of minutes, you'll be changing by 0.8, okay? I represent x, and then your y-intercept will be the 25. So that means that if you didn't study anything at all, you'll at least get a 25. I don't know if it's points or percent, because it did not tell us if it was points or percent for the test grade, but you'll at least get a 25, all right? So that's your equation. If it needs you to interpret it, the way you could interpret this is that for every minute of study time, you'll get a 0.8 increase of score, all right? And then if you got 0 or got no study time, you'll at least get a 25 points or percent. That's how you would interpret it. The question did not ask us to interpret it, so I'm not going to do that. But at least I'm going to mention it. The next one says identify and interpret the residual for a student that studies for 1 hour and earned an 80. So they earned an 80. This is actually what they got. All right? So this is their actual score. We need to try to evaluate any residuals in between. To evaluate that, guys, I need to use my predicted value or my predicted equation to calculate what we should get with 1 hour of study time. All right? So I would write y hat is equal to 0.8. So again, the x represents that study time, and they said 1 hour. However, our model isn't evaluating hours, it's evaluating it in minutes. So we need to convert this 1 hour to minutes, which is 60 minutes. So I replace this with 60, then plus 25. So now I calculate. So when I multiply, I would get 48 plus 25, which is 73. This is their predicted score. So this is what we predicted. So based on what we predicted and based on what they actually got, did we underpredict or overpredict? Well, we underpredicted because we predicted a lower value than what they actually